Consider the standard model of network communication. Two distinct nodes, Alice and Bob, exchanging data packets across a standard connection. To protect this data from passive eavesdropping, we apply symmetric encryption. This effectively locks the data, ensuring only those with the correct cryptographic key can read the contents. But an active man-in-the-middle attacker doesn't need to read the contents to cause damage. They simply intercept the transmission. A sequence of encrypted data blocks is intercepted and reordered by an intermediary. Because the keys are perfectly valid, the receiving node successfully decrypts the manipulated blocks. The mathematics worked flawlessly, but the out-of-order plaintext blocks reassemble into a corrupted final message. Protecting data from being read does not protect it from being rewritten. To guarantee data integrity, we need dedicated authentication protocols. To understand exactly how an attacker exploits this, we have to look at the mechanics of a specific block cipher stream. This animated diagram shows electronic codebook encryption. Plain text is divided into discrete blocks, independently converting into corresponding ciphertext blocks. Because each is encrypted on its own, they have no relationship to their sequence. In transit, an attacker actively swaps the second and fourth blocks. The receiver then executes the standard mathematical decryption algorithm on these newly swapped blocks. The system raises no alarms. The ciphertext itself is mathematically valid under the shared key, so the decryption succeeds. Algorithmic decryption success is a dangerous false proxy for data integrity. Relying on encryption alone leaves the system blind to structural tampering, which is why an independent layer of verification is required. The solution to the integrity problem requires separating the act of authentication from the act of encryption. This logic chart introduces the message authentication code. Feeding a plain text message and secret key into an algorithm produces a fixed-size block attached to the message. The receiver mirrors this process with a local key, calculating a new code. A direct comparison confirms authenticity. From an engineering perspective, this raises a question. Why would a system authenticate a message without also encrypting it for confidentiality? The first architectural use case is network broadcasting. Encrypting individually for hundreds of nodes wastes resources, whereas a single MAC can be efficiently verified by anyone holding the correct key. The second use case involves environments with heavy network loads and massive amounts of traffic. These systems save time by randomly sampling authentication tags rather than performing full decryption. The third use case applies to executable code programs. These must remain plain text to run rapidly, but they require strict pre-execution integrity checks to ensure no malicious code was injected. The MAC provides a lightweight, mathematically rigorous proof of origin and integrity, avoiding the computational overhead associated with strict confidentiality. We can expand this toolkit further to accommodate networks that need authentication without relying on a shared secret key input. This animated diagram illustrates a cryptographic hash digest. It is the fixed-length output of a one-way mathematical function applied to a variable amount of data. Unlike a MAC, it maps any variable-size message into a uniform digest independently of any cryptographic key. This layout details three authentication architectures. Option A wraps the hash digest in a symmetric encryption block, leaving the main message in plaintext. This proves authenticity because only two specific parties share the symmetric key required to verify the encrypted digest. Option B wraps the hash digest in an asymmetric private key encryption block, creating a digital signature. This eliminates the need to distribute secret keys. Anyone possessing the sender's public key can verify the transmission source. Option C concatenates the plaintext message with a secret value before hashing it, creating a keyed hash MAC. The secret value is never transmitted, making it impossible for an attacker to modify the intercepted message and generate a valid replacement hash. Decoupling the secret key from the hashing algorithm itself provides engineers with flexible architectural options tailored to different network trust models. A hash function's utility relies entirely on surviving three specific, rigorous mathematical attack vectors. This diagram defines the first property, pre-image resistance, or the one-way property. Given a specific hash code, it must be computationally infeasible for an attacker to reverse engineer the original message that created it. The second property is second pre-image resistance. Given a specific block of data, an attacker cannot find a different block that produces the exact same hash. This strict rule prevents data substitution attacks. The third property is collision resistance. Breaking these properties requires exponential brute force effort, roughly 2 to the power of n operations for pre-image resistance, and 2 to the power of n divided by 2 operations to break collision resistance. These three properties combine make digital forgery computationally infeasible. They transform a simple data fingerprint into an unbreakable cryptographic guarantee. We can see these theoretical mathematics operating in a finalized, secure enterprise system environment where user data is protected. The standard Unix password scheme is a practical, everyday application of secure hash functions. This animated diagram shows what happens when a password is created. The system never stores the plaintext. Instead, it combines the password with a random string of characters called a salt. A salt is an additional layer of random data designed to complicate brute force guessing attacks. This combined string passes through a deliberately slow hash function before the resulting digest is stored in the user database alongside the plaintext salt. Because the hash is pre-image resistant, an attacker who manages to steal the entire database still cannot reverse those digests back into usable passwords. These exact same hash properties are used in intrusion detection systems to baseline files and immediately alert administrators to any unauthorized modifications. We use symmetric encryption as a locked box for confidentiality, MACs as keyed tags for proof of origin, and hashes as unique fingerprints to detect tampering. Robust information security requires isolating specific threat models. We use encryption strictly for confidentiality, while relying on the mathematical certainty of MACs and secure hashes to guarantee authenticity and integrity.